Hello everybody, this is Cameron Snow with Danomics.com. This is going to be another video in our Danomics Basics series, and in this one we're going to cover how you can calculate water saturation. We're going to go over a few of the most common methods, and we'll discuss how you might go about choosing those and what are some of the parameters that you'll need to set as part of that. So let's get started. So by this point in your interpretation, you should have already gone through and done all your log cleanup. You should have repaired it for washout. You should have already calculated your clay volumes, your TOC, and your porosity. If you've not done that or you don't know how to do that, you can go back and check out some of the previous videos. Once you have those calculated, then you're ready to move on to your water saturation. So with respect to calculating water saturation, there are several methods that are available to you. So for example, we have the standard Archie formulation. We have the Siemens-Dew and modified Siemens-Dew formulations, Indonesian, dual water, and Waxman-Schmidt's. These all have their specific use cases. When you're dealing with relatively clean reservoirs or low clay reservoirs, Archie's formula is always an excellent starting point. And you really have two places that you can go there. You can do an effective saturation or a total saturation. And that's driven by what porosity you want to use inside of that equation. I myself typically go with the total porosity. But if you're working clean sandstones, you're really going to get a very similar answer with either the effective or the total. The Siemens-Dew methodologies, those are more suited for when you have higher clay reservoirs. In these cases, you're going to want to look at what is the resistivity of your clays, so you'll have an additional parameter that you need to set. Indonesian is often used for fresher waters, and dual water is often used for when you have perhaps a bound water component that has significantly different chemistry than the mobile formation waters. So we'll hit on a few of these and talk about how we might set some of these parameters. One of the things that you need to know how to do, or that you need to understand when you're calculating water saturation, is the role that the picket plot plays. The picket plot, it's one of my favorite plots in all of petrophysics. It's a very simple plot, yet I find it quite elegant. So your picket plot is typically a plot of your total porosity on the y-axis and your deep resistivity on the x-axis. These are both going to be in log scale. And when you look at these, typically we draw lines of constant saturation across here. And these are straight lines in log-log space. And so this line represents where we have 100% water saturation. So any data that falls on or to the left of this point would be considered to have no hydrocarbons in it. And then as we move to the northeast of this line, we start to get to lower and lower water saturations. Now the intercept of the 100% saturation line with 100% total porosity, that is essentially the resistivity of our formation water. The slope of this line is defined by the M exponent, that's the cementation exponent in Archie's equation, and the space between these lines is determined by the N exponent, that's the saturation exponent in Archie's equations. So when we're using the picket plot, we can use it to help us establish these parameters if we perhaps don't know them from things like fluid measurements or core measurements. And we also want to use this plot to really interrogate our reservoir intervals. So a lot of times we'll filter the data that's shown on this plot to only what meets our reservoir criteria. So for example, if you're looking at sandstones, you may put on a cutoff that restricts the plot to only having cleaner intervals that meet a certain porosity threshold. And we can show you, how that affects the plot here in just a second. The other thing here is that we typically do this on a zone by zone basis. So we would want to, look at this plot on a zone by zone basis and understand, how this works. And we also want to consider the context of the adjacent zones. For example, we don't want our the resistivity of our formation water to be jumping all over the place as we move from zone to zone. So we'll consider that as well. All right, so how do we go about getting started? Well, the first thing that you need to keep in mind is that when we're looking at this, we're going to be looking at it in the downhole formation temperature space. So the first thing we need to do is we need to get our geothermal gradient and our surface temperature correct. Up here in Wyoming, surface temperature is a little bit cooler. It's going to be somewhere, let's say, around 60 or 65 degrees. Your geothermal gradient, of course, this can spatially vary, but in this particular area, we're looking at a geothermal gradient of about 1.1 degrees per 100 foot. So once we've done that, we've got our temperature correct. And then what we'd want to do is start bringing in some outside data into our interpretation. So for example, do we know anything about the resistivity of the formation waters from this area? This is something that's easy for you to measure. Go out there, collect a sample at the wellhead, take this back to the lab and analyze it. This is a test that only costs a couple $100. It can be done very quickly at a wide range of laboratories, and this can really help you nail down part of your analysis. Alternatively, if you know roughly the salinity of your formation waters, a lot of people think in salinity instead of RW, then you can look at that as well. So, for example, here we can see that, with what we've put in now, the salinity, we would assume is about 66,000 parts per million. You can also use the picket plot to help you set this data, and we'll discuss how you can do that a little bit. I happen to know from this area that the RW measured at surface was about 0.15. So we'll put that in here. That's RW at surface. That gets converted to the downhole temperature. And now we've got our picket plot, which is updated, and our saturation is updated as well. So that's one of the first starting spots that we'll have. After that, we need to consider, do we know anything about the M or the N values? M and N can be measured in the laboratory through electrical test on core. This is often quite expensive and quite time consuming to measure. And so you'll find that a lot of times this gets overlooked. I wish more companies would run electrical tests on their core, but a lot of times this just gets cut in the budget. However, there is hope. There are ways that you can use the picket plot to help you here. So let's filter down to a couple of formations. So let's say we're interested in the Teapot and Parkman formations. So once we've selected those formations, and let's say we only want to look at what meets our reservoir criteria here. So let's say at V-clay less than or equal to 40%, and at our total porosity greater than or equal to, let's say, 6%. So once we filter that out, it cleans our plot up a little bit here. What we see is a trend here that we might be able to assume is a wet trend. If nothing else, we don't want all this trend to be greater than 100% saturation. And we can use that as a justification for adjusting our M value in this case. We need to decrease the slope here, so we're going to set M at 1.8. And as we do that, we see that we are adjusting our water saturation here. We can see, if we zoom in here to the Parkman and Teapot and look at our results, we can see how that changes as we move to lower M values. All right, so now we can see we're putting a substantial amount of hydrocarbon now into the Parkman and teapot formations as we adjust this interpretation. Now, another thing to notice here is that these are quite, we do have some quite clay-rich intervals in here. These are lower shore face sands. So often we have a little bit of upper shore face at the top, and then we have a lot of lower shore face sands where you have a lot of interbedded and interspersed clays. So that may call for a different method. So often I start with an Archie-Feti method. So we'll set that here. We see what our saturation profile looks like. The next step would be to say, all right, let's customize that method a little bit. Let's say we wanted to consider a Siemens-Dew method. So we'll go with a modified Siemens-Dew for these two formations. And as we do that, we see we now have another parameter that we need to set. And this parameter is our RT clay parameter. Okay, so as we toggled to Siemens-Dew, let's toggle back and forth here. So here's a Archie total porosity. All right, and here is a modified Siemens-Dew. All right, so we can see the modified Siemens-Dew puts more resistivity in here. Now, what we'll need to set is we'll need to look at the resistivity of our clays. So we'll go to our RT clay cross plot. We'll want to remove that filter because we're actually interested in looking at the higher clay portion of the spectrum. And instead of restricting this to just two formations, we'll put on all our formations here. And we see that the resistivity of our clays as we move out to the higher clay intervals is about somewhere between 3 and 4 ohms. So our default here isn't bad. We're at about 4 ohms. I think it could be a little bit lower. We're going to set that at around 3.3. We could, of course, adjust that on a zone-by-zone basis. But as we move the RT clay lower, it puts more hydrocarbon into our reservoir. As we move it higher, it'll remove calculated hydrocarbon from our reservoir. Okay, so that's how we can go about setting our RT clay parameter. Let's go back to our picket plot here. One thing to note is when you're looking at a picket plot for high clay intervals, what you'll often see is as you move to lower porosities that you'll actually start to see the trend to go vertical here. And that is something that's quite common with higher clay systems where you actually have a bit of suppressed resistivity, especially in the tighter intervals. Okay, so that's how we can set that. One of the questions that I get quite a bit is, hey, how do we use a dual water saturation? So I want to cover how we can set the parameters for that. So dual water poses quite a challenge because we don't know, what the bound water resistivity is. That's something you can't really measure in a lab, so it's a bit tricky. And there are some parameters that you need to set for that. So let's say instead of, our modified Siemens-Dew, we wanted to look at a dual water solution. So as we make this change, we'll see our resistivity profile change again. Now, what we need to do is we need to set that bound water resistivity parameter. The way we do this is we can look at the RO that we calculate, and we can look at that against our resistivity. And we really want to see in some of the shaly intervals, we want to see these values overlap. So we can find, a plain inorganic gray shell like we have down here in these formations. And we can start adjusting our resistivity of our bound water parameter. And what we want to see, we want to see the RO and the deep resistivity curves start to overlie one another. Okay, so we'll adjust that a little bit higher, and you essentially just want to get this dialed in until we see them almost laying on top of each other. So we're almost there. And you'll notice now we've got what I consider pretty much a perfect match down here in these inorganic shell intervals. And when we come up and we look at our target zones here, we can see how the resistivity profile has been affected. We can see that down here now in these shaly intervals, we have added more hydrocarbon saturation. And that's because we're saying, hey, the bound water here is, is affecting our saturation calculation. So we're trying to correct for that. And if we come here and we update our saturation track for to have the shading match what we may consider our cutoffs to be, we can see that we're now highlighting where we may have some more hydrocarbons in here. So starting to put some more saturation here in reservoir that looks a bit less conventional. So this is that, as we're starting to get into those lower shore face sands here, we can see some of the challenges here. And depending on how we wanted to dial in that interpretation, we may put, some more pay down here as well, where we still see some elevated resistivities. I'm going to switch back to the modified seam dew, and just once again to show you the difference in that. Once again, now in modified seam dew, we can see that we have an elevated, hydrocarbon saturation profile, or, I should really say decreased water saturation profile throughout here. And you could see that now, we would actually start to calculate pay down to a much more significant interval here. And this is actually played out in reality. We've actually seen a lot of operators start to drill these lower shore face Parkman sands and get good wells out of them. This is something that EOG has been doing for years. And so it makes me tend to believe that an interpretation similar to this one is more correct. All right, so once you have explored your saturation methods and you've decided on those, you would repeat this type of analysis zone by zone, where you would try to set your RW, hopefully from data. You would adjust your M and N values, and you would decide what methods that you want to use. Now, the RWs that I have are from, down here in the Parkman and Teapot formations for this area. Up shallower, I think we have significantly fresher waters in this, and that's what our RW apparent is telling us as well. And so we could actually adjust our saturation here to have, some much lower salinities to reflect those fresher waters that we have, and use that to really update our saturation profile through here, because it's very likely that a lot of this is not something that actually has hydrocarbon in it, and we want the interpretation to reflect that. And once you've got this set zone by zone, then you may want to consider looking at your permeabilities. Now, permeability is something that I think is always dangerous to interpret unless you have some core data. And if you have core data, then you can really start to dial this in. However, I do briefly want to hit on a few of the methods here. So we've got a number of built-in methods here, like Wiley-Rose, Coates, Timmer, and Tishier. We also have the Heslop method built in. All of these are very similar in that they take 3 parameters, a P, a Q, and an R parameter. And when we look at the form of this equation, it's P times some combination of porosity and saturation, and then this is taken to the R power as an exponent, with Q being an exponent on porosity in most cases. And there are slightly different variations in this. When we look at the difference between Wiley-Rose and Timmer and the Tishier methods, what we see there is, they use some different units. One used, let's say their units in percent, the other used it in decimal. That's why we see some different exponents there. These are all empirical methods, so they were doing a calibration to their local field studies, certain types of rocks. So be cognizant of that. These are just empirical correlations, so you would expect to use different exponents than they did anyway. Coates tries to account for the difference between effective and total porosity, so trying to count some clays in there. And Heslop, did his work specifically on tight rocks. So you'll notice some significantly different exponents when using his methods. I always like to start with Wiley-Rose. I think it's a very simple method, works quite well on clean reservoirs. And I've actually noticed that with a lot of lower permeability methods, you can really a lot of times just come in and just set the P parameter in here to dial that back, and often you can just drop that by an order of magnitude. So say from 25 to 2.5, and then of course you just need to come in and maybe make your scale something that's a bit more relevant for unconventionals here. So let's say we're going to go from 0.001 to 1 millidarcy here. So then you can come in and you can start seeing that profile. And in a lot of unconventional plays, you're actually going to see permeability down in the nanodarcy range. So you'll need to have a lot more zeros in front of that track setting. But basically the P variable here can be viewed as a shifter, so you can shift your interpretation left to right. R can be viewed as one that will stretch or squeeze your data a bit. I find those two the easiest to set. I think Q can be a little tricky to get used to, as the relationship is often a bit inverse to what we see with the R parameter. But once again, that's something you want to have calibrated to core. So you may have a good feeling for what that is, so you can probably get in the ballpark with just changing the P parameter, but to really dial that in, you'll want to adjust multiple parameters, but you're going to want to be constrained with core. All right, so that's it for this video. Just remember a high-level overview. Start off by bringing in whatever actual real measured data you have. Make sure to get yourself calibrated with respect to the surface and downhole temperatures. Once you've done that, you can turn to your picket plot to help guide you on your other parameters here. You want to do that on a zone-by-zone basis. And then you also want to tailor the methods you're using to the rocks that you're working with. So cleaner reservoirs, you're going to want to consider, maybe an Archie saturation method. It's always a good place to start. For shalier sands, you're going to want to consider something like a Simandou. And if you think that you have a reason to investigate things like bound water, you may want to turn to something like a dual water formulation, although with the caveat of knowing that that can be quite hard to calibrate just due to the fact that we can't measure all the parameters that go into it. And if you're remember, if you're working with Simandou, you're going to need to set that resistivity of clay, so you have a second cross plot that you need to look at. All right, well, I hope this was informative for you. If you'd like to learn more about, calculating water saturations, and you'd like to start doing this in your own interpretations on a zone-by-zone, well-by-well basis, let me know. You can always reach out to me at sales@danomics.com. Thank you.